So now we're going to do this kernel debugging. So we talked about this. So, and the Windows 11 machine I've been given out is fine. Windows 10 is fine. And you can do it on Windows with ARM or Windows with Intel. And I'm going to do it on Windows with ARM here. So remember, the user applications sit here, and normally if you want to access a kernel function, you call kernel32.dil, which is in userland, and that's the normal Windows API. This is the native API that normal developers are not expected to use because it's not thoroughly documented, but internal Microsoft people use it, and advanced users and malware authors use it directly. And then this goes to the kernel, which is NTOS kernel, in the kernel, and it then accesses things like device drivers to work with the hardware. So let's take a look at that NTOS kernel. I go to C Windows System32. And by the way, everything strange in Windows is because of history. And you might notice that we're still using a System32 folder, even though it's a 64-bit version of Windows. That's why everything has so many strange names. It's all history. There's a time when these names made more sense than they do now. All right, Windows System32, there we are. And NTOS kernel is in here. I can probably use search. There it is, all right. And now I should be able to examine it with CFF Explorer. Yep, all right. And this lets me see information about it. And I can see the functions. If I go to the export directory, here's all the functions that are available. And see, a bunch of them have just numbers, but here's some with names. And there's a bunch more with names. Can initialize rule violation, query report action, and just on and on and on. There are many, many functions. This is the Windows API. These are the kernel functions that do everything. Everything you do ultimately ends up calling one of these to do it for you. All right. And that's, I think, all we wanted to see there. So now we can use WinDebug. All right. Now we need to do local debugging. Let me get this so I can see. There we are. All right. So we need to enable debugging. I think I have already done this on this machine, but let's check. I need an elevated command prompt or terminal would be fine. Run as administrator. There we go. And then I can do BCD edit. And you have to turn debug on. There's probably some way to see if it's already on, but I don't know how to do it. Well, let me just try that. Let's see if I can. BCD edit. Store import. Copy, create, delete. V. Displays entries in full. Okay. Display order. Debug settings. Sets the parameters. Enables. Debug enables or disables. Yeah, but it's not obvious how to see the settings. Anyway, this is what you have to do. BDCD edit debug on and debug settings local to enable local debugging. I think it's already done in this machine. If not, we're going to find out. And you have to restart after doing that. So, all right. By the way, this happened to me when I did it. So let me, in fact, check to see if it's going to happen on this machine. All right. I'm going to go through the steps because now I think I used my machine at home to develop this project lately, and I probably haven't set this one all right. So let's try it. It'll also be interesting if this error occurs. BCD edit /debug on. Okay, that completed successfully. And BCD edit debug settings local. All right, those both completed successfully, and that's good. That means it's probably done in this machine. I'll try to go ahead without restarting. But when I did it on my machine at home, I got this warning. An error occurred when trying to modify the settings. It's protected by secure boot policy. If you have a Windows 11 machine that you made on ARM, in the default way, it will probably have secure boot turned on, and you have to turn it off. And you can find it in your settings, in your virtual machine settings. There is a secure boot option that you have to turn off. This is a big deal, and if you listen to Paul's Security Weekly, we talk about secure boot all the time, because Paul works for a company that tries to secure boot. Secure boot is a relatively new feature, and there are a lot of problems. There are a lot of weaknesses, so you can do bad things even when secure boot is on, and But anyway, so we'll run WinDebug X here. That's just an easy way to get it running as administrator, I think. All right, and now we can do File, Attach to Kernel. Last project we just did, we attached to a userland code that we just wrote, but now we're going to attach to the kernel. Now, you can attach to the kernel a lot of different ways. You can attach to another machine over a COM port or USB or network, but we're going to debug the local machine here. So we just hit the local tab and say OK. So we're just going to look at the kernel of the machine I'm using, which means we can't use breakpoints, because this machine has to keep running or it'll freeze up, and a breakpoint would freeze up. But you can do you can at least examine the kernel without modifying it. So we can start with LM, and here's all the loaded modules. You see a bunch of them, and here's the one, NTOS kernel, abbreviated NT. That's the one with symbols, that's the kernel, and here's all drivers and other things. And most of them don't have symbols.
So forgive me, a naive question.
Yeah.
We are exploring the virtual kernel.
That's right.
Okay.
Yeah, in this virtual machine. Yeah, because outside it's a Mac, but that's right. Yeah, it's exactly right. It's the kernel of the OS running in this virtual machine. All right, and so you can use this GUI if you like. If you click the NT link, then it will show you more information about NT. LM, that's what it did. It executed this command. And all these links do is type out command line commands for you. It's kind of silly. But anyway, you do get some information, and you get more links showing you more information about them, and you can get the functions in the kernel by clicking the Functions tab. And now, this is why I feel like it's really stupid to pretend this is not a command line utility. You get a list of all the NT functions that begin with A, which is far too much to fit on the screen. And if you scroll back, you get a letter. You can click the start letter and get the one starting with P and so on. This is very not useful. Just doing the command line commands is far more likely to get you what you want. But anyway, that's the sense in which the new thing has a GUI. So you can also see the command it used to do that. If you go back to the start of here, maybe this. There we go. See if this gets me there better. They don't seem to be in order. Okay. There we are. Here's the command. XDFNT bang P star. That's what this was. That was an examine command with some kind of flag or something like sorting or something. So anyway, that's what it did. And you can use help. There's local help in the ribbon, which is by far the most useful thing. This opens the Windows 3.1 chum files left over from before Windows 95, which is one way to express help. And this is what happens inside Microsoft. Different teams use different help message tools. But this is what the WinDebug team used, and this is where you really learn how to use WinDebug, that thing. All right. So you should learn how to use the examine function. It's the thing you use most often, just like dir is the most common command in the command prompt. You examine to find out what's going on. So you should read this thing and learn how to use it. And then you'll be able to search for things. And one thing you'll be able to find is there's something called warbird. One of these functions has warbird in the name. So you'll be able to find it and find the flag on this one. And that's the same on ARM and Intel. So then we're going to disassemble a function. Now there is NT create file is one of these. In fact, let's start by just searching for it. If I do examine NT bang star create file star, I'll find that there are a few create file functions, but one of them is just NT create file. So I can unassemble that one with UF NT bang NT create file. And now I see the source code for it. And here, you notice in my example here, this is x86, or Intel source code. But in this machine, this is ARM source code, because I'm running on ARM. And it's fine, but of course the source code is different. The functions have pretty much the same purpose, which is why you can run the same app in both versions of Windows. But the code is different. So now I can search for memory. and I can search for something and find it. Now, this particular search probably won't work on ARM. I'd probably have to do something else. But I can see the pattern of bytes here shows like A4F1. I could probably search for that. I could search ntbang, ntbang, ntcreate file, and then length 100. That's just how far I'm going to search. And now I'll search. Remember, the bytes are in little endian order, I think. So I think if I wanted to find this, I'd have to put 38 and then 33.
E8.
Oh, E8, thank you. E8, then 33, and then let's do zeros. Good. Zero. Oh, something bad happened. Okay. Then 0x00. Let's see what that does. That should work. And it did find it. It found it at F140, F1A8, and there it is, F1A8, there it is, E833. Okay, so as you can see, it is working. You can search for patterns of hex this way. And it found it at the expected location, and this is a 64-bit address. They put an apostrophe in the middle, which I appreciate. So here's the first 32 bits and the last 32 bits. And, all right.
So the first 32 bits are the same for all the commands?
Oh, yes, because the kernel is not that big. So, in fact, a lot, this A420 is probably always the same too. The whole kernel is not very big. That's why we were talking last time about how rootkits work. You can spot bad addresses in the service set descriptor table because they should all start with the same few characters. And if you point to something like in userland, it'll be wildly different, so it'll stand out. Yeah, all the kernel functions are in a certain region. In fact, I think if I do LM, I think it showed us that. Let's see. If we go back to NT, yeah, here's NT. It's FF800 A3 to FF800 A4. That's the whole kernel. So it's pretty small. Yeah. All right. Good, important point. All right. And so anyway, now there are just some challenges. If using Windows 11 on ARM, here's the search I did. Oh, good. Another. I did put one in here. I just demonstrated one, but here's another you'll see just to show that it works. And now you can find strings if you like. So I can go again, just length 100, so it won't take too long. I can do, remember, if you use the help message, you can learn about the search function, and there are these switches, and this SA will find all ASCII strings in a region. So this is going to go starting at this location, ntcreate file, which is the start of that function. It's going to search the next 100 bytes for ASCII strings. And this 100, I think it's hexadecimal. I think it's really 256, but I'm not sure. Anyway, there it is, finding things, and see, it just finds unprintable junk that happens to be readable. There are no actual readable ASCII strings in that range. And if I want to, I can search for longer ones. If there were any, this on the Intel processor, there is a longer one. And this one, there's not one that's 6 or more, but I could restrict it to look for ones of a different length. I think they're all, here's 3 and 4. It looks like all I have is lengths 3 and 4. Let's try looking a little further. Let's look for 1,000 bytes and see if we find anything. Okay, there's a longer string with a quote in the middle of it, which is kind of screwy. All right, anyways, now, and here, okay. So I wanted to show you what happens if you make it, it's minus bracket L6. So you put bracket L6 in here. That's why you really have to read the help message. The syntax of these commands is not obvious. This is going to look for things that are 6 or long, and there it is. There's one that's 6 long. And I'm a little confused about a quote in the middle. I kind of wonder exactly what happened. I guess that means there's a quote in there, and these quotes don't count, but it makes me a little nervous to see a quote in the middle of a quoted thing. Anyway, I guess it's literally a quote.
So if it is longer than 4, it breaks down into 2, 3 plus 2.
No, no. If it's long, it just comes long. No, I think what it means is the string literally contained a quote. But I'm a little, that's not obvious to me, and if I wanted to find out, I would go look at it in hex to make sure. Yeah, good. Anyway, all right, and so, anyway, good. Oh, actually, that's fine. All right, and so you can find the word magic in NT, and you see, you have to search through quite a bit of it, but then you'll find there's a string containing the word magic, a flag there, and now we can display memory. For example, let's find out about this thing with a quote in it. I want to do DB. I think I can just put in this address. I'm not sure it'll work. Oh, good. And there it is, 7, oh good, it worked, 7H plus quote. It is 7H, it is a quote. 22 is a literal quote. Okay, so that's nice to see. Now DA shows things as ASCII. If I do DA, it'll show me only the ASCII stuff. If I do DB, it shows me both hex and ASCII, and there's another option that shows you just the hex. But DB is usually the most useful.
Unicode, I think, is the other option.
DX or?
The Unicode, ASCII Unicode.
Yeah, there is ASCII Unicode. Yeah, that's right. There's also Unicode. But anyway, DB is most useful just like HXD. It shows you the hex and the printable characters. All right, and so you can now examine a straight structure like here's a file object. Remember, a file is an abstraction. I was just teaching this in another. File is an abstraction, an illusion for the user. You know, bits are on the disk, and some group of them are called a file, and here's the actual structure called a file. This is the data object that makes it, so it's got a type and device object that it's on, and context and pointers, and somewhere it should have a name. Yep, file name, there it is, Unicode string, and on it goes. So, you know, you have all these bits of information are what creates the file abstraction. And they're also read access, write and delete access. The permissions on a file are part of its structure. All right, and you can view the running processes with .tlist. Notice the wild inconsistency. Some commands start with a dot, other commands just have a letter. This is the world of Microsoft. I say really need to read that help page because this thing is not logical or easy to understand. You really have to read the help page to learn how to format these commands. But anyway, tlist shows me the currently running processes, which are just the usual sort of thing. The same thing you'd see in Task Manager. All right, and so we can find out more about the LSASS process. That's the Local Security Authority system, so it's always running. It was used to log in. And so it's always running, and you can get more information about it with bang process. So now we have commands that start with X, commands that start with dot, and commands that start with bang. And I don't know the difference. So here we get a lot of information about the process. We get its process environment block, its parent, I think process identifier, I'm not quite sure what the CID is, the object table, and so on. You get various things about it. All right. And there's a blue address bar for more information. Click the blue address in PEB. Okay, so we can examine its processed environment block by clicking that. And here you get a lot of data. Here's some raw data there. And this stuff is pretty complicated. I'm not going to go into any detail of it, but you get a lot of information about what it's using. I think these are all the libraries it's using. Yep. So again, this is the stuff you'd find in Process Explorer. You get that list of all the libraries it's using and so on. So, all right, you can examine device, node, and driver. This will tell you about the physical disk you're using, and you must be using some kind of hard disk, or I think an SSD counts as a hard disk. Here you are. So here's my physical disk, and notice I'm using a SCSI disk that is VMware Virtual. So I'm seeing the virtual disk here, which is connected by a virtual SCSI port. So it thinks it's using a hard drive. Of course it's not, but that's what it's being simulated as. All right, and so now just to find a flag, there's something you have to find here by searching for these bytes. On Intel, if you're on ARM, you have to search this, and then you'll find the flag, because of course the ARM assembly code is different. Anyway, that's what I wanted to show you about this one. That's good, clean fun. Kernel debugging, and just like with IDA, we've only scratched the surface. We've just done a few common commands. The experts, you could have a whole course in WinDebug, and you could have 2 or 3 whole courses on the kernel. So we're just getting the essential parts of it. All right, let me stop this one.